Good morning, students. So today we have come to the end of this unit, and we are going to discuss on Fermi's theory of positron. It was introduced by Richard Feynman. Richard Feynman, he was an American theoretical physicist. He belongs to Jew family. He was very famous for this picture, the theory of positron. And of course we know that Dirac introduced antiparticles, and this is a continuation of Dirac's theory. Richard Feynman, he considered Dirac as a hero. Dirac considered Albert Einstein as a hero. Albert Einstein considered Maxwell as a hero. So the hierarchy is going on. Richard Feynman, as I said, from US, very famous scientist, and people ranked him as 7th famous greatest scientist of all time. He introduced path integral approach of quantum mechanics, then electrodynamics, theory of electrodynamics. In fact, he got the Nobel Prize for theory of electrodynamics in the year 1965. Then he introduced the theory for superfluidity of liquid helium, and also he gave a lot of lectures, and those lectures were combined together and brought up as a book, Feynman lectures on physics. Very famous. 1 billion books had been sold. Feynman lectures on physics. Also, he was very famous for introducing nanotechnology. So in the year 1959, he gave a talk in the Parliament of US, and he introduced this word, there is a plenty of room at the bottom. He introduced this sentence, there is a plenty of room at the bottom. It means that lot of technologies are there when you are going down, when you are going into the atomic scale. So he introduced nanotechnology. We are living in the nanotechnology, which was introduced in the year by Richard Feynman. So introduced nanotechnology, lot of things. So that's why he said he was considered as a 7th rank physicist, greatest physicist of all time. Richard Feynman, he was born in the year 1918 in New York, and his father was a sales manager, her mother was a housewife, homemaker. And when he was born, for about 3-4 years, he could not talk at all. And the relatives of his daddy, they said that you will have to make him to have curiosity on all the things. So his father, he showed everything with a curiosity, just asked so many questions. So slowly he started talking. His mother was, as I said, she was a homemaker, and usually she will crack lot of jokes. So he gained the humoring sense from his mother. He learned the knowledge from his dad. In the schooling, he was very good at mathematics, especially calculus. He was so good at calculus in the sense every time he used to think about new ideas or the introduction of some letters in calculus. For example, we have d by dx. He used to write as d's, d apostrophe x. For sin x, he will write some other symbol. So he was so interested in calculus. Every time he used to think only calculus. This made his second wife to depart from him. This made. So his wife departed from him, and she said, while getting divorced, and she said this word, every time he thinks only calculus. He became the theoretical physicist. So you have to think always. For theoretical physics, always will think and do. So as I said, in the school he was so bright, in sense only in calculus. Then he finished his schooling. Then he joined Columbia University. He did not get the admission. He applied for Columbia University, and as I said, they belong to Jewish family. So there was a limited seat only for the Jews. So in Columbia University, they said that you are not, you will not get any seat here. So immediately he went to MIT, Massachusetts Institute of Technology, and as we know that immediately he would join only mathematics. So because he was so clever at calculus, so he joined mathematics. So after that he realized that I could solve all the problems ahead. Even second semester problems, third semester problems I can solve. So if I study mathematics, it is of waste. So immediately he thought. So he rejoined engineering. Then after that he realized again that engineering also not fit for him. He joined physics. So he graduated in the year 1939 with physics degree from MIT, Massachusetts Institute of Technology. Then after that, his parent and himself, they wanted to join. He wanted to join for master degree and connected with PhD. And they chose Princeton University. So Princeton University was very, very famous university in which Albert Einstein was there. In fact, Niels Bohr later he came. Albert Einstein was there. Wolfgang Pauli was there. John Newman. A lot of scientists were there. So he joined under Dr. Wheeler. Dr. Wheeler, who got a lot of ideas, physics from Niels Bohr. So he joined under Wheeler. Wheeler was very, very famous person for black holes. Black holes will always, it will absorb energy, it will never re-emit energy. So these words were uttered by Wheeler. So Wheeler and Richard Feynman, they joined together and they worked a lot. So that was the World War time, and we know that Oppenheimer, he ordered him, and in fact he talked to him through the phone, and why can't he join the preparation of atom bomb? So immediately he joined. He did lot of calculations about making of uranium, plutonium, uranium 235, 238. He made a lot of calculations and how much energy it can come out. So he prepared every theoretical work, and in fact it worked out. It worked out with a little boy and fat man, which were dropped in Hiroshima and Nagasaki. We know already this. So this was theoretically done by Richard Feynman. So this is called the Manhattan Project. So after that, he joined Cornell University, US, and for longer period he worked. Then he went to some other countries. Again he worked as a professor. Again he came back, and the year 1988 he passed away due to some cancer problem. Now, after 1950s, he was considered to be the topmost scientist, physicist in the world, first physicist in the world. Whereas in 1900s, as I said, he was ranked as 7th greatest physicist all time. So Richard Feynman introduced this picture, which we are going to see now, about the theory of positron. Okay, what we call this as Feynman diagram. So we are going to look into the Feynman diagram, and this is about theory of positron. Okay, and as I said, this is a continuation of anti-particle, antimatter. And Feynman diagram introduced because we know already about, we can easily grasp the ideas if you show some pictures. Instead of equations or instead of derivations, immediately if any picture is there, then immediately we can grasp the ideas, correct? So that's why he introduced a Feynman diagram. Suppose if two particles interact, you consider electron, okay, two particles, electron and positron, doesn't matter. if two subatomic particles, if they interact and they will release exchange particles. So first one, I repeat, two interaction of particles, they release exchange of particles. Exchange of particles are nothing but, it can be either gluon, photon, meson, so they are called exchange of particles. So this interaction of particles can be done by means of Feynman's diagram. So Feynman's diagram represents the pictorial representation of interaction of subatomic particles. Okay, we will see later. So for every particle there is a corresponding antiparticle, such that when the particle and the antiparticles interact, a complete annihilation takes place. So we have already studied about when we are doing about antimatter, antiparticle. So we know this line very well. Both of them vanish, releasing the energy in the form of light photon or in the form of creation of a new particle. So this also we know, annihilation and pair production. Annihilation and pair production. Particle and the antiparticle with the same mass, same spin, but they have opposite charge. So going for E minus, then this will be E plus. Okay, have opposite charge, opposite magnetic moment, and so on. Electron has an antiparticle, so-called anti-electron. What we call this is positron. The electron is represented by E minus and the positron is represented by E plus. So as I said, this is exchange particles. So when this is the pictorial representation, we have to remember it's very simple idea. Feynman diagram is very simple idea. Two subatomic particles, when they interact, they will emit exchange particles. Okay, it's very important thing. Exchange particles, it can be either gluon or photons or bosons. Okay, for example, when you take charged particles, it will emit electromagnetic waves. So for electromagnetic waves, nothing but photons. So all the photons, when you are thinking about, immediately you can consider as a wave nature. Okay, so this is an exchange particle, representation of exchange particle. Exchange particles, when two charges they annihilate and they will emit photons. Okay, is it very simple to remember? And when you are going for any strong nuclear force, so we will have to think only exchange particles as gluon and mesons. So exchange particles for nuclear strong interaction is nothing but the spiral wave. Okay, spiral one. And this is for bosons, weak particles, weak nuclear forces, bosons. And all fermions, electrons, protons, all fermions are represented by this arrow. Okay, all antifermions are represented by opposite arrow. So remember all those things. We are going to use these arrows only in the Feynman's diagram. Okay, this is pictorial representation of interaction of two subatomic particles. Okay, or many subatomic particles. Is it okay? Very simple one. You are going to use. So representation of particles by lines. Arrow left to right implies particles go forward in time. So they go forward in time. And arrow right to left implies particles go backward in time. It doesn't mean that it's back in time. No, doesn't mean. It is just to differentiate from fermions to antifermions we have used. Okay, doesn't mean that the particles go back in time. No, it is not like that. Okay, so just to differentiate, it's conventional method. Conventional, for example, why should we keep left on the roads? So this is conventional one. We always go on the roads, we always keep on left side. So this is conventional method. So similarly, this is convention. And similarly, when you are going for any circuit, in the electronic circuit, we always go with the arrows from high potential to low potential, from positive to negative. It is conventional. Actual current goes from negative to positive. Actual current. So this is convention. Okay. Similarly, we have a convention of fermions and antifermions. So this is for particle and this is for antiparticles. Okay, antiparticles. And when you are going to draw the diagram, pictorial representation, there must be x-axis and y-axis. And space and time will be your x-axis and y-axis. It can be on the other way around also. We can go with the time here x-axis as x-axis, and we can go with space as y-axis. Doesn't matter. Both are the same. Okay. So pictorial representation of any subatomic interaction of subatomic particles will be represented in terms of space-time graph or time-space graph. Both are the same. Only thing is how you are going to choose. Space as x-axis doesn't matter. Time as x-axis doesn't matter. Both will give you the same result. Okay. So now this is your x-axis as space and this is your y-axis as time axis. Look at the arrow. So it means that the time progresses very fast. What of the x-axis, space? It remains the same. So particle at rest, but it's moving very fast. See, a particle moving instantaneously from one point to another point. Okay, and similarly this one also, particle is at rest. And what are these 2 points? These 2 lines, they refer for a particle, and this one refers for the antiparticle. They are progressive with respect to time. So they move with respect to time. They forward in time. The particle moving forward in time and space. So this line represents for a particle which moves forward in time and space. It is not a trajectory. So usually when you draw in classical physics, you will always go with the trajectory. It is not trajectory. It progresses. It moves. Okay. This is back in time. It is not back in time. It is just a convention. So this is for the antiparticle and this is for the particle. Particles and antiparticles, they move forward in time and space. Just the convention is arrow marks. That's all. Is it okay? Now this is the Feynman's diagram, and the title is Feynman's diagram for a positron. Correct? First we'll learn for the electron. Then it's easier to convert into positron. First we'll learn for electron. It's very simple pictorial representation. Very simple one. So the behavior of interaction of subatomic particles is visualized by a Feynman diagram. So first point, interaction of subatomic particles, which is represented in terms of Feynman diagram. Okay, this is a visual tool to understand the interaction of subatomic particles. This will work out only for the subatomic particles, not for the gravitons. See, gravitons are exchange of particles between 2 galaxies, between 2 planets, stars and suns. Okay, but gravitons are not subatomic particles. So this will not work out for gravitons. Very important one more question. Is it okay? Now, so first we will go for electron. Okay, this electron E, so this is E minus. Okay, we will consider this arrow mark is for a fermion. So this fermion, it moves forward in time and space. It moves forward in time and space. Space is considered as x-axis. Time is considered as y-axis. Now look at this. The particle moves in forward in time and space. Now this point is called a vertex point. At this point, it will emit some radiations. It will emit some photon. The photon also goes like this. That also goes forward in space and time. The moment when it emits, immediately the electron will lose its momentum. Correct? Surely there will be change in momentum. So electron will go this way, again forward in time. This is for the past and this is for the future. See, past, electron is at the past, electron is at the future. I repeat. So as I said, this is called exchange particles. Exchange particles are nothing but virtual particles. Sometimes we call this as virtual particles. For electromagnetic radiations, we will call this as photons. So this is nothing but a photon. I repeat, electron, it moves forward in time. Okay, and at the point vertex, exactly at the vertex, it emits some radiations and there is a change in momentum. So the electron just moves ahead, again forward in time. So this is the pictorial representation of emission of electron. Is it okay? Emission of a photon. Okay, for the electron. Is it okay? Now we'll go for electron which absorbs a photon. Now we know that any photon which comes somewhere here. Okay, any photon which comes here. And electron is also forward in time, correct? Is it so? Is it so? Is it forward in time or back in time? Forward in time or back in time? Forward in time. Forward in time. See here, time axis here. Okay, back in space. Back in space. This forward in time. So it means the photon, it gains the energy and it goes somewhere here. It absorbs the energy. It absorbs the photon and goes somewhere. So this electron will have more momentum. This electron will have less momentum. Is it okay? Charge is conserved, energy is conserved. In all the process, everything is conserved. Is it okay? So this is for the absorption and this is for the emission. So Feynman diagram is only for subatomic particles, as I said. Feynman diagram describing emission and absorption of an electron. Any doubt? Okay. Now we will go for proton. So next slide is nothing but for the proton. So as I said, this is for the electron, which just now we have looked into, and this is for the positron. Okay, this is for the positron. For whatever the rules for the electron, that will also rule for the proton also. Okay, so they are all subatomic particles, they are all fermions. So now we'll go for the positron. See, positron, as I said, this is backward in time. So we'll have to change into this axis. Okay, arrow has been changed. It is not back in time, as I said earlier. This is just a convention. Okay, so positron also moves forward. So this is just a convention. So at this point vertex, it will emit some photon, and proton will have less momentum. So we'll have less momentum. So automatically we'll have this diagram. Is it okay? See here, you have a positron. At the point vertex, it emits some radiation, energy, photon, or virtual particles, okay, or exchange particles, and immediately the momentum of the positron will reduce, and that shows this picture, this line. And when you are going for a positron absorbs a photon. So as I said, that this photon, which meets the positron and it absorbs, and the momentum of the positron is gains little bit and it goes somewhere. Okay, so E plus gamma, which will give you again E plus, but charge is conserved. Only thing is momentum is changed. Okay, so Feynman diagram describing emission and absorption of a positron. Now electron positron annihilation. So we are going to have now two charges. So electron and positron, they meet together and they annihilate and they produce a photon. Okay, look at this E minus. This is E minus stands for the electron, progresses forward in time. Okay, what are this one? So back in time. So electron and the positron, they meet together at vertex and there will be an emission of photon. Okay, so they annihilate and produce energy. Okay, they join together, they annihilate and produce energy. They combine together. Similarly, at this point, so electron and positron pair production. When photon comes here at the point at vertex, it will produce electron and positron. So that's called pair production. Okay, so energy produces matter and antimatter. Here matter and antimatter produces energy. Just opposite. One is for pair production, another one is for annihilation. So this is the Feynman diagram describing interaction of an electron and a positron. Now we will go for interaction of two electrons. So we know that when two electrons they combine together. So what will happen when two electrons combine together? They will repel each other. When two electrons when they come closer, surely they will repel each other. So we will consider two electrons now. This is first electron, and we will consider this is as second electron. You can also draw the graph between time and space on the other way around, as I said earlier. Time can be here and space can be here. At the time the whole picture will be changed. Okay. So now we just consider this is first electron. We go to consider This is a second electron. So now two electrons, they meet each other. When they meet each other, surely they will repel each other. This we know already. Suppose we consider first electron, they come here. Okay, when they come here exactly at the point, vertex point, it will emit some photon, it will emit some radiations, we know. So this electron, and after emitting this photon, it goes somewhere here. So this is representation of the first electron after emitting photon. Is it okay? Now this electron, when it is nearby, it will absorb this photon. It will absorb this photon and it will gain the momentum and it will go somewhere. So two electrons, when they combine together, they will repel each other, and with the help of the exchange particles, again they will go like this. So this is something like this. See? Is it okay? So Feynman diagram describing interaction of two particles, out of which we can draw a lot of picture representations for all subatomic particles. Like gluon, we can go for gluon, or we can go for mesons, even WZ bosons, weak interaction particles, beta decay. So everything can be done with the help of pictorial representation, which was introduced by Richard Feynman. So people could understand easily. So that's the reason. And this is a simulation which I have taken from the internet. So thanks to internet. So I will say, and this is time axis and this is your space axis. See, you just consider the two electrons, they combine together, and at the point vertex, it will emit some radiations and it will go somewhere here. Okay, this radiation is absorbed by the second electron, and that electron goes somewhere here with the gain of the momentum. So momentum is conserved, energy is conserved, charges also is conserved. So Feynman diagram of two electrons interacting electromagnetically by the exchange of a photon. So exchange of a photon. So very good simulation I have taken from the internet. Okay. So now we can, this is for your exam point of view. You have to write all the points for the exam point. Okay. So Feynman diagram is a representation of a quantum field theory processes in terms of particle interactions. Okay, subatomic particles. So this will work out only for the subatomic particles. Very important thing is not for gravitons. Very important one mark question. Okay. The particles are represented by the lines of a diagram, which can be straight with an arrow opposite also, or without, depending on the type of the particles. The lines in a Feynman diagram represent the probability amplitude of a particle to go from one place to another place. So arrow means probability amplitude. In Feynman diagrams, the particles are allowed to go both forward and backward in time. Forward for particle, backward for antiparticles. When a particle is going backward in time, it is called antiparticle. It doesn't mean that particles move back in time. It doesn't mean, just a convention. In 1940s, Richard Feynman developed a diagram technique to describe the particle interaction in space and time. Feynman diagrams represent quantum mechanical transition amplitudes, and of course it gains the energy, that is, it absorbs. So any electron which will absorb the energy and will go to the excited state. That's the first one, absorption. And second one will be, after the absorption, it has to emit some radiation to come to the ground state. So emission. So absorption and emission. They appear in the formula for cross sections and decay rates. More specifically, Feynman diagrams correspond to calculations of transition amplitudes in perturbation theory. A Feynman diagram is a two-dimensional representation in which one axis, usually horizontal axis, chosen to represent space, while the second one represents as time. Space-time contains two fields, the electron and the photon. So we can also go with time and space, or time and vice versa, doesn't matter. Both will give the same results. For example, time as x-axis, space as y-axis. We can also keep space as x-axis and time as y-axis. Both will give you the same result. The electron and positron annihilates the photon. Photon can convert it into an electron and a positron pair. Annihilation and pair production. Okay, we know that annihilation and pair production. These things are possible provided they should have conservation of angular momentum and the electric charge should also be considered. As I said, charges also should be considered. The exchange of photon between the electron can cause the electron closer to the exchange of a photon may push them apart. So we have seen as a simulation. The electrons can exchange many photons at different places at different times. So this will not only work out for single electron or a single proton, this will work out for many electrons. Sometimes photon annihilates the electron-positron pair, then creates a new photon which may interact with the another electron. So it goes on like a cascade process. It is not for a single electron, it goes on. We call this as a loop. Feynman diagrams transcribes the different possible evaluation of quantum fields at a given situation. So main assumptions of and requirements. Time runs from left to right. So this is just a convention. Okay, left to right convention. From right to left for antiparticle, left to right for particles. Particles are usually denoted with solid lines or gauge bosons with the helical and dashed lines. We have already seen right from the beginning. So arrow directed towards the right indicates a particle, otherwise it is antiparticle. Arrow this side is antiparticle from right to left. Points at which 3 or more particles meet are called vertices. So vertex where the emission will take place as well absorption will take place. Okay, at vertex. At any vertex, momentum, angular momentum and charges all are conserved but not energy. Okay, so that is the end of the whole unit, and in this class we have seen the very important one, the pictorial representation of interaction of subatomic particles. So this is represented as Feynman diagrams. Feynman diagrams are very famous diagrams. So especially when you are going to study particle physics, it will work out. So particle physics and introduced during 40s. So especially when he was doing his PhD, in the thesis he introduced electrodynamics, very famous, for which he got Nobel Prize. He shared with other two scientists in the 1965. So very famous man, Richard Feynman, who introduced many things in physics, especially in quantum physics, quantum mechanics. Okay, thank you students. We'll start.